Hello, welcome back. In this segment, I'm going to talk about a quiz problem given to our grad students at the University of Maryland, College Park. This is an AES related problem. I will explain the problem very briefly and then talk about the solution. Okay, so um, we are given two plain texts, M1 and M2. They look pretty much the same except the least significant byte. For example, uh, this plain text has all A's. This plain text has all A's, but the least significant byte has, uh, instead of A, we have B. Okay, so A's are replaced by BB's. That's basically what we are saying here. The question is, if we apply AES on a message M1, we get some ciphertext. Similarly, if I apply AES on message M2, we get some other ciphertext. So we wanted to ask, what is the difference between the ciphertext after round one? Just after round one of AES, what will be the difference? How many bytes of the output of AES may differ at most between these two messages? Even though we just have only one byte changed. By the way, this is all in hex. Okay, so if you count this, you will see there are 16 bytes, which means 128 bits. That's exactly the bit length that we can encrypt using AES. At any moment, AES can be used to encrypt only 128 bit of data. Okay, this is something I would like to refresh. All right, so here's more of a formal way of saying, okay, here is your message M1. You are calling AES using key K, and you will get some ciphertext. And we are doing the same with a message M2 using the same key K, and you get ciphertext C2. The question is, what is the difference between the ciphertext C1 and C2 after round one, just after the first round? So in order to solve this problem, we would need some understanding of how AES is actually working. So I will show you a slide which I got from the book of Professor Parr and Pelzel, Understanding Cryptography. So I will make use of their slides to show you the structure of AES and then talk to you about the difference between the ciphertext after round one. Okay, let's go. Sorry, here it is. So this is the book that I was talking about. We are not going to talk about all the AES details. Okay, I will just quickly show to you the most important ones needed for solving this problem. Okay, so as I mentioned earlier, AES takes some input data and gives you back some output. Of course, input is 128 bit, output is 128 bit. You can have keys of different configuration, 128, 192, 256. Okay, and here is the high level structure of AES, right? I can zoom in a little bit further. What you're seeing here is that your plain text 128 bit first gets mixed with a key. There is some key K, and I'm not going to talk about how the key scheduling algorithm works. We don't need to know for this particular problem. Imagine some keys mixed with your plain text, basically XOR. So you get some random looking data at this point. And then it goes through the byte substitution layer. What it means is that it's like a substitution cipher that we talked about in the other video. You know, each byte will be substituted by some other byte. Okay, there's something called S box in AES that does that substitution. Okay, you feed in a byte A, you may get some other byte. You feed in another byte, you get some other byte. There are some mathematical properties. We don't need to know how the substitution layer actually works for this problem. And then we do some permutation, that the shift rows is basically permuting the output, and then mixes the output. Okay, we talked about the Hill cipher in the other video segments. So the idea of Hill cipher is part of the mixed column layer. So you will get some gibberish at this point, and that gibberish is again XORed with the new key. Okay, so AES does this again and again. That's why you see round one, round two, round NR. NR is the number of rounds. Number of rounds is a function of the key size. If it is 128 bit, you see 10 rounds. 192 means 12 rounds. 256 means bit key length means 14 rounds. Okay, this idea of doing this pattern again and again is something Shannon proposed very early in 1940s time frame. Right, you take weak ciphers, like substitution cipher itself is a weak cipher because patterns are revealed, as we talked about. And we also talked about mixed Hill cipher, for example, that diffuses the data. Each of these building blocks are actually insecure, but his idea is to put all these insecure building blocks together, apply them multiple times, so you get something really difficult to break. Okay, so you get a nonlinear equation to solve with so many unknowns. That's basically the underlying idea of all these block ciphers. Okay, of course, there's a lot of creativity involved in designing the substitution cipher, mixed layer, and so on. For this problem, it's not necessary to go into all the details. Okay, all right. So let's now look at the um, problem in this view. This is much more useful in my opinion. As you can see, we have 16 bytes of data. Our data gets substituted first. Each byte gets transformed into other byte using a substitution layer. Okay, so you get some random looking data, meaning each byte gets substituted by some other byte, and then those bytes gets mixed up. Okay, so now let's talk about our problem. We had all A's in the first input, right? Okay, so let me write it here. So what did we have? We have A everywhere. We have A here, A here, A here. Okay, so we have all A's here everywhere. All right, which means that the substitution layer will substitute everywhere A by some other thing. So of course, all of the B's will be same because its inputs are the same. Okay, and then the shift rows basically mixes up our data. Okay, which has no effect because our inputs are all A's everywhere A's, right? That's for the first message. But what about the second message? What did we do? Okay, I must have said it's AA here because two ASCII characters make one byte. Okay, AA, right. So we have this situation now. We need to compare this behavior with, let me finish this first, AA and AA. So this is the first message. For the second message, we replaced AA. This AA gets changed to BB. So the question is, what is the difference here? What will be the output somebody will see if they change the last byte here, AA to BB? That was the question. Okay, so it's easy to see what happens now. Since I changed the last byte AA by BB, this byte will be different, right? Okay, now where is this byte going? This byte is going into the mix column. Okay, so as you can see, if you follow the arrow mark, right, it goes to the mix column. Okay, so we need to understand what is the mix column function is. Okay, as we can see, mix column somehow produces 4 bytes of output here. Let's think about the definition of mixed column. Mixed column is actually defined as a matrix multiplication in AES. There's a predefined matrix. AES has a matrix. I'll show you the content of the matrix in a moment. But we multiply a matrix with a vector, column vector. So where is this? What are the elements of this column vector? Whatever you see here, this B15 is coming here. So there will be B15 here. Okay, only talking about the mixed column for the first block. And we have B0, okay, B5, and what about this one? So these are the 4 bytes. So now let's think about matrix multiplication. If you multiply a matrix with a vector, you get a vector. Okay, what is the purpose of matrix multiplication? All these 4 bytes gets mixed up, right? If you recall how matrix multiplication works, you can do it multiple ways. One way is go by row, right? Another way is go column by column, whatever you like. So if you now take the first row, you're multiplying the first row with all of these 4 bytes to get the first element here, right? Whatever element here is a linear combination of B0, B5, B10, B15. What about the second row? You take the second row, you again multiply with all of these. That means this is also a linear combination of all of these. So your C0, C1, C2, C3 that you're seeing here, all the 4 items, is basically dependent on B0, B5, B10, and B15. Okay, what it means is now is that since I changed AA to BB, so I'm changing only this byte. Okay, even though I changed only 1 byte in the input, now all of the 4 bytes of the output will be different. That's because of matrix multiplication. So to answer the question is asking us how many bytes will be different after the first round. At most 4 bytes will be different. Okay, that's the answer. All right. And very quickly, I wanted to show to you the official matrix that is defined as part of the AES, which is not needed for this problem, but it's good to see it. So it takes your B0, B5, B10, B15, multiplies with this matrix to produce C0, C1, C2, C3. Okay, this is an invertible matrix. And the multiplication is all happening in a particular mathematical structure, but you get the idea that if you multiply a matrix with a vector, you get another vector. And each element C0 depends on B0, B5, B10, B15 because of the matrix multiplication. Okay, this is basically called diffusion because you want each byte to depend on all other bytes. Okay, that means if you change a byte, all other 4 bytes will be changed. That's the beautiful idea that the AES uses, which is actually interestingly found also in the Hill cipher that we talked about. Okay. All right, that's basically it. Thank you very much for your attention.